Okay, maybe the internet's back on now. In which case, I can try and do some stuff. Sisyphus. Let's see what's going on with Sisyphus. Was that in 2D or 1D? Forces. 5.2. Um, Give me a second, please. Okay, so Sisyphus is pushing the thing up a ramp, and we know ramps look like this. We know there's usually an angle theta here, and we want to find um, D and E, which says find expressions for the force Sisyphus needs to apply to the boulder to get it to begin moving. Another way of saying that in physics language is to say we need to overcome F static max. Okay. And so if we had a free body diagram of the boulder, I guess that's the active objects. We all have our normal force, and we have the force of gravity, and there will be a push up the ramp. I'll call it FP, and static friction would point down the ramp. Okay, so this would be the free body diagram of the rock. And the next step now is to, I guess, we'll just go back a second and make sure we're talking about the right dimensions. So did I label any axes yet? No, I didn't. So I can call this plus y, and let's call up the ramp plus x. Okay, so now I can do a sum of forces in the x direction, and that means I need to go and look at the free body diagram and tally up all the forces that are acting in the x direction. Okay, and make sure I see which direction they're going. So I have F push, that's going straight up the ramp. And then what's going down the ramp are a component of gravity, right? And I can see right away, I've done this 30 times now, that it should be equal to Fg sine theta, and also there's static friction. And if everything's in equilibrium, then that should equal ma, or it always equals ma. If it's in equilibrium, it will equal 0. Okay. And now I need to, all I need to do is see that F push is going to need to be greater than both of these two things, right? If I bring both of these over to the right-hand side, then I'll have F static plus Fg sine theta. And as long as F push is, okay, it's frozen on there. try, it looks, I'm getting it on my, it seems to be transmitting okay from my end, and I'm receiving it on me. So maybe just, if it's frozen for you, try and reload, or yeah, just reload the page. Um, yeah, I guess it's not perfect, not a perfect technology solution yet, but we got it. We can do what we can. Anyway, so all of these things on the right-hand side, those are the forces acting down the ramp. I have F static and a component of gravity, and as long as F push is bigger than that, then we should be able to um, start pushing up the ramp. I guess this is this one here, F static. That, of course, has this maximum value, F static max, which is given by mu static times the normal force. And we could figure out the normal force, again, by looking at the free body diagram and seeing all the forces acting in the y direction. Sum of forces in the y is going to be Fn minus Fgy. And since we have no acceleration in the y direction, then this will equal 0, and I'll have Fn equals Fgy, which is just going to be mg cosine theta. Okay, so then I could take this and plug it in for that into Fn. If we have someone else pulling on the rope or pulling on the rock also, then all that's going to do is add another complication to the free body diagram. So, sorry, no, F push is us pushing, or sorry, is Sisyphus pushing against the rock, right? This is F. In red, I have F, the force due to friction, and in green, I have force push. So force push would be if we're standing here and we push up the ramp. Static friction will be pointing opposite to that. Okay. Where was I? What was I talking about? Down here, if there's someone else pulling up the ramp, then I have all of these same forces, F static and F push, but all I'm going to do is add another one, which we can call tension. Okay, sorry, it's a little messy. Let me clean it up. There's an arrow, and a tension arrow would just be also in the same direction, up the ramp. Okay, and back to the drawing, that would look like, well, I'll draw another version of it. That would look like, there's our boulder, and the rope would be like this, and there'd be some guy up here, Tantalus in fact, pulling on the rope. So that would cause a force going up the hill. And I don't think, I mean, then at this point we start having a whole lot of terms in our sums of forces, so it would get a little bit more, there would just be more complications in the math, but it would all be doable. I'll see if I can, if I might have some answers for that one written out, and if I do, I'll try and put them up online. But ideally, the best place to get them is when you go to the workshop hours. I'm not sure what you mean by do those forces cancel each other out. Whenever you say do those forces, please be specific and say which forces you're talking about, right? We have 5 forces here. I don't know which ones you are referring to. Um, okay, we can come back to this later. Let me move on to answer Aisha's question back here. Could you please explain question number 3 on the midterm? What was that one? Yeah, okay. Question 3 just involves using what you know in a totally new situation. Um, there is an object that falls down, and normally this would be an object in free fall. But since we have this fan over here applying a force in that direction, the object is going to have some sort of other shape going on. In fact, it would look like the trajectory would look something like that, a little bit more complicated. But we can figure it all out, right? Because we know the x motion and the y motions are going to be independent. And I guess we'll jump to the end of it. The whole point is when it hits the ground, it's going to have some velocity in this direction, right? It's going down. It has an x component. That would look like this. Vx, it has a y component. Vy, together they would be the 2 components of the total velocity v. Okay. And in order to find what the question was asking for, find the direction of this final velocity vector, and then I say find a way to calculate theta based on the parameters of this setup. I can see if this is angle theta, that tangent of theta is going to be equal to opposite over adjacent. That's the definition of tangent. And the opposite side is equal to Vy. The adjacent side is equal to Vx. So I need to figure out what Vy and Vx are for this object after it undergoes this fall. Vy is fairly straightforward because we know that the only force acting in the y direction is gravity. Okay, and in this case, to find the final velocity after falling, what do we start from the height h? Yes, we start from the height h. I can do a number of things. I think the most straightforward would be to think about v final squared equals v initial squared plus 2gh, and v initial would be 0, and so I'm left with v final, and this is the y direction, is equal to square root of 2gh. All right, so I can write that in over here, just keep tabs of it. Vy is going to be equal to 2gh. Vx is a little bit, requires a little bit more work. Figure out Vx because I need to figure out 2 things. I need to figure out the acceleration in the x direction and how long it's in the air. Okay, acceleration in the x direction is, of course, always going to be given by the sums of forces in the x direction times the mass equals, so F equals ma, second law. And I know that the only force acting in the f direction is this, what we call F fan. So acceleration in the x will be equal to F fan over m. Okay, and now that gives me A. So I'll be able to take this bit here, and I'm going to be able to plug that in there, but I still need to find t. So how long is it in the air? In order to do that, I need to think again about the y motion, right? Because I know that this will be true. Y equals y naught plus v naught t minus 1/2 gt squared. I can solve this for t. I know that the initial y is h, final y is 0, initial velocity is 0, and that term stays the same. So solving for t, I get t equals square root of 2h over g. Now I can take that and put it in for t. Okay, so when I do all that, I get a new equation for the velocity in the x direction after it falls. That will look something like this. F fan over m times root 2hg. All of this now gets to go in there. All right. And I'm probably not going to be able to write it so small there, but I'll try. F fan over m root 2h over g. And then that looks kind of complicated as is, but as a few people have already asked me about, we can simplify it. And if I simplify it, I'll get something that looks like, well, I can see the 2's are going to cancel, the h's are going to cancel, the g's are going to both go up, and the m is going to go up, and I'll have m times root g over f fan, which equals mg over f fan. Okay, and that should be what I wrote on this sheet. Let's double check. Yes. Tangent of theta equals mg over f fan. So to get theta, I just need to do the inverse tangent of mg over f fan. And this will give me the angle. We'll go back to the very original picture. This will give me that angle right there, that theta, which is another way of saying now we know the direction of the ball as it hits the ground. Okay, that should be pretty good for that fan, or there, I'll give you 10 seconds to ask a follow-up, otherwise I'll move on. I can zoom out and see it all in one now. Okay, great. Then let me go back up here. How do we get 444? This is a kinematics question that involves 3 different regimes of motion. Right, we have a accelerative regime, then we have a constant velocity, and then we have another accelerative regime, and we just need to figure out how far it goes in each one, and each one is just going to require a different application of essentially this expression, x naught plus v naught t plus 1/2 at squared. So for the first regime, I'm going at 3 meters per second squared for 4 seconds. Sorry, accelerating at 3 meters per second squared for 4 seconds. I assume I have an initial velocity of 0. So all that's going to do is involve this part. I can see right away the x after the first regime will be 1/2 3 times 4 squared. So that's 1/2 times 3 times 8, which is, no, sorry, 16, or 3 times 8, which is 24. So that's how far it goes after the first bit. The second bit, again, we'll just apply this same expression, except we have some slightly different changes now, right? It has an initial velocity. That's the biggest change because after this section, we're going at some speed. Exactly how fast we can do by this. So v equals at for 4 seconds at 3 meters per second squared. That means I'm traveling at 12 meters per second. Okay, and that's going to happen for 30 seconds. So the distance traveled during the second regime will be 12 meters per second for 30 seconds, which equals 360 meters. Okay, so that's how far it goes in regime 2. Regime 3 would look something like this. Let me just get the numbers right. We're going to spend 10 seconds slowing down. So I need to figure out acceleration based on that. So I know that my initial velocity, my final velocity will be 0. My initial velocity is 12 minus at. T is going to be 10. So I'll get 12 over 10 equals negative a, and a therefore equals negative 1.2. Okay, so that's the acceleration that it's going to take to slow down the train in 10 seconds. The next step is to figure out how far that will be, how long of a distance does that take, and again, we'll just use this same exact thing. So x equals v naught times t, which is, that will be 12 meters per second. I'll just do the letters up here, plus 1/2 at squared. So this is 12 times 10 minus 1/2 1.2 10 squared. And I don't have a calculator with me, but let me see. That should come out to be uh, 60. Yeah, I get 60 meters for this regime. So add up all three of these and you get 444. Okay, so that should be good for, oh, perfect, 60, yes, thanks, for that one. And so all it is, summarize, it's 3 different regimes of motion. Okay. Okay, so it looks like next on, I guess I'll go back to the rock. And it seems like there's a few questions around here all about the rock. So um, why in the mid-term? Okay, so I guess the difference between Sisyphus and this midterm question is the main difference is friction. Okay, so in the case um, in the case of Sisyphus, now we're including frictional forces. All right, which makes everything a little bit just slightly more complicated, but it's all still doable. And so not only in part D do we have to apply a force greater than the x component of gravity, we also need to deal with the fact that there's static friction. Okay, let me try and just redraw it neatly. Here's our boulder. If the only force acting was gravity, that would be down, oops, like this, and there would be a component of gravity. I'll draw it in gray that points down the ramp. Okay. And in the case of the question on the midterm, all we were doing was having to push up. I'll change the color for clarity. In red, we'll make a nice upward push there. So that would be the force push. This is Fg. This is the Fgx. Our force push just has to be bigger than this Fgx. Or it has to be, sorry, I should be more clear. It has to exactly equal Fgx in order for us to have non-accelerative motion. Okay, so this would enable us to move the boulder with at a constant velocity, as long as we pushed with the same force as Fgx. If we pushed more than Fgx, then we would start accelerating up the hill. And so now in the case of friction, we're going to add one more force to this picture. And friction gets, if you remember, like it increases as the harder we push until it reaches its maximum value, in which case we sort of break all those bonds that are tying the piece of material to the floor, whatever the molecular stuff is that's going on there that we don't care about, but is really underlying all the physics. So all this means is to, back to this drawing, is that we have to push a little bit harder. Because now we have to beat both of these forces in order for it to go up the ramp. Okay, so I would hesitate, F push and F friction, if I'm answering this line right here, F push and F friction, those aren't the whole story, right? We also have this Fgx there. Okay, so that needs this, the F push is going to have to cancel, or I don't want to say cancel, but F push is going to have to balance Fgx plus F static in order to get this thing to move. Okay, great. Have I gotten everything that's on there so far? I think so. Okay. What else? Anything else? Question 5 back on here. Why is question 5 number A? I did that yesterday, I think, didn't I? That was like the first one from yesterday, um, which you should be able to go and watch. Just, I guess, the drawing I drew, if you just scan through the video, you'll see it looks something like this. There's two graphs, and the distance between the two positions are always getting bigger. The video only saved after it was restarted. Oh, okay. Well, that's unfortunate. Um, I guess, well, I'll give the explanation again and draw a neater graph. If I plot position versus time for two falling objects, the first one is going to fall and it's going to look something like a parabola shape like this. And that starts at t equals 0. And then at some later time, I'll say t equals t1. That's when I drop the second rock. And it should look exactly the same as the same exact shape as it goes down. And you can see, I'll do it in a different color. Everywhere along here, so this would be the distance between the two rocks, right, at this time t1. And then the next time, you can see the distance has gotten bigger, bigger, bigger each time. And more conceptually, another way you can maybe imagine thinking about answering it is just imagining how the velocity is of the first block. So block 1 and block 2, or particle 1 and particle 2. Particle 1 is going to be going faster than particle 2 at every position, right? So that means between any two sections in time, particle 1 has to have a greater velocity than particle 2, which means the implications of that is that it's going to cover more distance, or not cover, I'll say travel more distance in the same amount of time. So every second that elapses, particle 1 goes farther than particle 2, which means the distance between them should be increasing. Okay, so that should, I think that, I mean, that really covers all of this stuff. All right, so we got a couple backlogged here. Let me see, where are we? Can you go over number 6 on that worksheet, part C? Uh, okay. Let's see. I'm going to pull this apart so I can keep track of it. let's get some boxes. There's a box. There's a box. And I'll make this my hand. Nice happy hand. Okay. And if I drew the draw free body for each drop, find expressions for the force of block A on block B and the force of block B on block A. Okay, so I'll just draw these free body diagrams for each one. This one's block A, that's block B, and I'm gonna forget about vertical forces, just horizontal. Okay, there's no vertical stuff happening. So you see how I say I draw simplified versions also, where you only consider the horizontal forces. That will just make things a little bit easier. So there's two things acting on box A in the horizontal directions. One is what we're calling F hand. I guess that makes sense. And then there's the force of box B on A. Okay, so that would be the free body diagram for box A. The free body diagram for box B would have just one force, and that would be the force of A on B. Okay, and then all I really wanted to do in part C was to convert these to sums of forces expressions. So the sum of forces acting on box A is going to equal, if I call this direction plus X, there'll be plus F hand minus FB on A. Together, those are going to equal mass of A times the acceleration of A. Okay, and I could do the same thing for the sum of forces on block B, and that's just going to be F of A on B equals mass B times the acceleration of B. All right, and that's all we really know. I didn't give you any numbers or anything. Well, I guess I did. I said part B, if everything moves in an acceleration equal to A naught, then all I would do is just substitute that A naught in for AB and AA, and I would have my relationships between force and acceleration for each box. Okay, is there any other issues there with that, with those interacting objects? Otherwise, I'll go on what would be the FBD for the hand. Well, we draw a dot for the hand. And this is where, we start to have to, I don't know how to say, we get a little creative, or we have to interpret the physical world in different ways. But one possible free body diagram for the hand would be the force going this way from A on hand, and then also we have a force going that way, which would be the force of like your arm on your hand, right? How does your hand move? It's because your hand bone's connected to your arm bone. So that could be a free body diagram for the hand right there. And then the free body diagram for your arm would include include the force from your shoulder, etc. And that would just go on and on until you got to your feet. Okay. So I think that covers all of that one. Why is A the answer for number 10? Let me see. I forget what number 10 is. Didn't we do that one yesterday too? Number 10, it was, again, the plot. The plot is the best way to think of it. And we have an object that's going up at constant velocity. And then at that moment in time right here, the connection breaks between the object and the helicopter, at which point after the object is going to be in free fall. And so free fall is going to look like this. And so the interesting point that the question's asking about is right there. What's the velocity immediately after the break? Well, it has to continue on at the same velocity it had right before the break. If it didn't, then we would have a velocity diagram that looked funny. It would look something like, sorry, I should label my axes. That's V and T. This is the right situation. This is the right, or the, I guess, physically correct drawing. This is wrong down here. I just want to make sure to get this clear. This is the wrong version. If you're going up at a constant, oh, no, sorry, that's not V, that's position. Going up at a constant speed, and then if your speed changes all of a sudden, the slope here is going to have to do something weird, like break. This will be a discontinuous bit of line right here. Okay. And we can't have that sort of thing. That's problematic in nature to have things that look like this. Okay. Everything has to be kind of smoothly transitioning. The other thing to imagine is just sort of try it, like hoist up something with a rope, right? And then it's going up and up and up, and then then let go of the rope. The whole thing's going to continue going up a little bit, and then it's going to slow down before it gets faster and starts falling down. Okay. So that would be, I think, the answer for this. Yeah, plus V naught should be the right answer for that. Can I? We're going straight up. Yes, if I would, this is going straight up. The whole thing, sorry, still back on the helicopter thing. We are going straight up, right? This graph that I drew that looks like this. This is really, really important. This is a graph of something going straight up, right? The only variable that's changing is y, right? And y is pointing up. So this is the graph of an object that's going straight up. This is time on the horizontal axis. So just because it's there's a line here that's going off in this direction or to the right doesn't mean the object's moving in the right. It just means its y position is getting higher and higher and higher, and it's doing so at a constant slope. Right? So the slope of this thing is equal to the velocity. And I guess I could say that also the moment after the belt breaks, right there, that's when the belt breaks. You can see the slope has to remain the same just for a little bit, just for a little teeny moment. The slope at that part right there Oops, no. Well, crap. There. The slope right there has to remain the same on both sides of this. Okay. Then after it breaks, then the slope can start changing. So all along here, that's where we have changing slopes. Right? And that's because the object is accelerating, accelerating during this part. Okay, let me try and do this one. Where are we back here? Number 3 question, homework number 3, question 4. Goodness, homework number 3, question 4. Yeah, I guess, I mean, I can solve it. All this one is looking at is, let me draw a picture. We have some object that's being, let me just read it carefully. 2 kilogram projectiles launched from a launching device. It leaves the launcher traveling at some speed. The net force during the launch was equal to this. How much time did the projectile spend in the launcher? Okay, so I'm going to have to involve probably this equation and probably something with this equation also, right? These are the 2 things that come to mind when I read this question. F equals ma and v equals v naught plus at. This problem's asking me how much time did it spend in the launcher. This is where I'm going to get my time. Oh, that's homework 4. Oh, I'm sorry. Thanks. Okay. Homework 3, question 4. Oh, the pizza party. Okay. This picture is, I guess I'll redraw the picture. I don't need that anymore. Oh, that's a bad picture already. Here's the roof. Here's the ground. And I have this pizza particle that's going to slide off the roof with some initial velocity. After it slides off the roof, it's going to be in free fall, and it's going to make its way down to the ground. Okay, and we want to figure out this distance between the wall and where it hits the ground. All right, and we know a few things. We know this h, and we know theta, and we know v, right? I believe those are the things we know. We know its speed, we know alpha, and we know h. Yes. Okay, and so just briefly, this sketch. I'm not going to do all the math because this one has some involved, like, well, not terribly involved. You just have to solve a quadratic formula, which you can do, but the general structure of the solution is to figure out how long it takes to hit the ground, right? So I need to know what to plug into this expression in order to make that happen. So y equals y naught plus v naught t minus 1/2 gt squared. I know the final y is 0. The initial y is what we call h. The initial velocity is going to be, if I break up that v naught into components, right, I'm going to have v naught in the y and v naught in the x. And angle theta is, I guess I called it alpha in the problem. I should stick with alpha. Angle alpha is right there. So I know that v naught in the y direction is going to be equal to v naught times sine of alpha times t minus 1/2 gt squared. Okay, so now this is an equation that's not super easy to solve, but you can. It's a quadratic formula. Probably that would be a lot of work. I wouldn't expect you to do that on a test, but when you're at home doing homework or wherever you do your homework, then you should be able to solve a quadratic formula thing. And so h is a number. What is, I guess everyone has different numbers, but h is 4.8 for me. V naught would be 9.9 meters per second. Sine of alpha would be sine of 20 degrees times t minus 1/2 9.8 t squared. All of that equals 0. And you could figure out a number for t. Okay. And like I said, since everyone has different random variables in this, it's not going to make a lot of sense to solve it all the way out, do the math for it. But you're going to get some number for t. I don't know what exactly it is, but it's some number of seconds, right? It'll be like, probably, I think it's a kind of a small number, about 0.5 seconds. I'm not even going to write that because that's not the right answer, but some number of seconds. And once you do that, then you can figure out how far it travels in the x direction just by using x equals v naught x times t, right? Because there's no acceleration in the x direction. V naught x is just v naught cosine alpha, and whatever we get for t will go right here. Okay, so if you did it without using the quadratic formula and got the right answer, then great. There's probably, like I've said a dozen times, there's always 5 ways of doing these problems. Maybe there's another way without using the quadratic. I can't think of what it would be at the moment, but my guess is that you secretly did do the quadratic. It just wasn't obvious that it was a quadratic. But somehow you had to get this t. And I don't know, I'm not sure I see how else you can do that. Anyway, the solution for that, it's on there, right? You can go through and just see exactly everything I just did. And it should work out. You found the final velocity for Vy, and then plugged it into the kinematic equation to find t, and then plugged it into another equation. Yeah, okay, I guess with that, so you found this Vy down here. Yeah, okay, I guess if it works out, then awesome. I guess that would be it. I suppose that's another way of doing it. Um, uh, yeah, okay. Yeah, okay. So I guess I see what's going on, I think, and it makes sense. That should work too. Awesome. It's nice to have several ways. You can barely hear me. All right. Well, okay. Sorry. I'll increase my volume maybe, or I move the microphone closer to my mouth. That might be the biggest help. All right. Let me move on. Where are we? Can I go over problem 12 from the old midterm? What's problem 12? Yeah, sure. We could draw some graphs. And I'll just duplicate the plot axes real quick. This one has 6 different variables we want to plot, all as functions of time. We got, I think, x, y, vx, vy, ax, and ay, all as functions of time. And let me just reread it again. A bird is flying horizontally in the positive x direction at a constant speed. At t equals t1, she falls asleep and stops flapping her wings and can no longer provide an upward force against gravity. At t equals t2, she wakes up and continues flying horizontally. So we have sort of three regimes of motion that we need to plot. The first one is just straight horizontal motion, right? Horizontally in the positive x direction at constant speed. So that would look initially like this. So I should draw my little timelines so I know where these T1s and T2s are. So we'll call T1 right there, T2 right there. And it's good to do them like this so that all the graphs line up. Me too. So no, you can't hear. I'll turn up the audio maybe. It's all the I can't turn it up anymore. I'm basically eating the microphone, so I don't know. This is as best as I can do. I'm just going to keep going. I can hear myself on my own compute. Try with your volume. I can hear myself just fine on the on my other machine. Okay. Anyway, so where were we? The bird's flying horizontally in the x direction at a constant speed. So the beginning looks like constant speed, which is a straight line in the x direction. Not dotted. Would be a positive constant velocity. That means no acceleration in the x direction. Okay, and then at t1, she falls asleep, stops flapping her wings, and can no longer provide the upward force against gravity. And we're going to neglect air resistance, right? So makes things a little easier. So let's do the y bits first. So right now in the beginning, she doesn't have any y motion, right? She's just flying horizontally, so there's no change in the y position. Likewise, velocity in the y should be 0, and the acceleration in the y should be 0. And then at this point, t1, right there, that's when she falls asleep and stops flapping her wings. And so her y position is going to start decreasing, right? She's going to be an object in a projectile motion, essentially, right? And that means she has an acceleration of negative 9.8. Okay, and that would look like this. This would be negative g on the acceleration curve. The velocity in the y direction would be a linear straight line until between these t1 and t2. Okay, and the y position would, I guess, look something. I'm going to redo the y position and say she's flying at some height above the ground. Okay, that makes a little more sense. So that's her y position, and it's going to start going down in a parabolic manner like that. Okay, and we don't want her to hit the ground, right? She manages to wake up before she hits the ground, so at t2 she wakes up and continues flying horizontally. So that means she's going to be flying at some constant new height. That's a straight line. That means there's no y velocity, and likewise the y acceleration goes back to 0. And then nothing should have changed in the x motion, right? We're assuming there's no air resistance, so everything just keeps on going just fine in the x direction. Okay, the only interesting stuff happening is in y. Okay, so does that look like the drawings that I drew earlier? Let me just double check. Yeah. Oh, I stopped it at T2 in these drawings, but in the video now, I guess you can see what would happen after T2. That's T1 right there, and T2. Okay, so there's a little, that's the birdie flying. For number one, parts B and C, shouldn't the distance be less than if the squirrel can't make it to the second ledge? Um, D is, I want to make D greater than whatever I figured out in part B, right? I mean, there's several ways. It's kind of like, it's just like the bicycle problem, but there's that we did. There's always a few ways of conceptualizing it, but it's not very good. No, this is our two ledges like that. We're calling this A, and that B, and that D. And we figured out, based on this initial velocity, essentially how far the squirrel goes in the x direction in this amount of time, right? There's some amount of time it takes to fall from A to B. That height difference is going to lead to a time. That time gets translated to a distance, right? We want to make D, if we're designing this ledge so that naughty squirrels can't get on there, we want to make D greater than whatever this distance of the squirrel, like X squirrel, um, will be V naught times T. This D needs to be greater than that. Yes, the question says, so the squirrel cannot make it. Okay, so the squirrel's, just draw it again. The squirrel is going to be able to jump this far, right? Based on this initial velocity. If he had a bigger initial velocity, say in orange, then he might be able to jump farther. But he doesn't. He's got the one I drew there, V naught. And so I want to put D past this point. Okay, if I made D smaller, then uh-oh, I'm going to have squirrels, and I don't want them. Well, I like it when they're, in the parks and doing their own thing, but when they get too close to me, then I get angry. Okay, what else? Any other big things? I'm going to have to sign off in a moment, so maybe take one more if I can from someone who hasn't chimed in yet. Will my office hours be extended tomorrow for the exam? Um, uh, I mean, I guess I'll put it this way. I'm gonna be there in the morning and so forth, but I have things I need to get done, so I'll be available during my scheduled office hours and possibly a little bit before and a little bit after. But at this point, because I've been away for 2 days due to the snow, I can't. I have a lot of stuff that's backed up and I need to get finished, so I can't promise that I'll be available for extended hours. You can always email me tonight, um, and so forth. But I'll be there from 11 to 12 for sure. Those are my office hours, right? Yes, I'll be there tomorrow and come by. But I would also, it's also good to, not do physics right before the exam. Sometimes that's helpful. Okay. All right. Well, if there's nothing else pressing, then I'm gonna check out of here and um, I'll see you all tomorrow at 2 o'clock or before. Okay. Um, Take care. Thanks again for the good questions and enjoy your Wednesday. Okay. Bye.